So to prove this modified version of the residue theorem, well, we basically already have the residue theorem, which tells us about this bit here, the 2 pi I times the residues inside, the poles inside. So what we need to concentrate on is basically what happens at these points like this. So let's just examine in detail what happens when we carry out this contour integral. So the left-hand side, okay, so this is what we're trying to prove. So now, okay, write it out again. So what does this give us? So, well, it gives us the integral from a to x naught minus r of f of x dx. We'll consider this bit here later, plus this integral from x naught plus r to b. And remember, we're taking the limit as r goes to 0. So this is the first interesting thing. We recognize this quantity here as precisely the principal value of the integral of f from a to b. So this we can rewrite as simply, after taking the limit, principal value from a to b of f of x dx. So this is useful in itself. Basically, it's telling us that integrating through a pole and using the residue theorem will automatically give you the principal value of the integral. Okay, so then let's just concentrate on this bit here. We can assume the rest of we'll concentrate on this bit later, and I'll just be lazy and just write, well, plus the integral over the rest. And just concentrate on what happens here. So at that point, if we change variables, we've got plus, so this point here, we've got z equals x naught plus r times e to the I theta. So we've got limit as r goes to 0 of and I'm going to change variables and make just dz. So r is fixed, and I've got okay, ir times d theta. Okay, so I've got I coming from there, r e to the I theta d theta, and I'm integrating around here. So I have to be careful, I'm doing a clockwise integral. So clockwise integral I can think of as minus the anti-clockwise integral. So just because I'm used to doing anti-clockwise integrals, I'll write it from 0 to pi, and okay, I can write it from pi to 0, okay, and then we're just going to swap the sign a bit later. So pi to 0. Now recall that if I've got a singularity at x naught, it means that I can write f of z as a simple pole. I just assume it's a simple pole. z minus, now I've got a simple polar x0, so it's x0 plus a0 plus, and then the Taylor series, plus etc. Okay, so I'm going to use this result in here. So let's now just concentrate on evaluating this integral. So I'll get rid of this for the time being, and we'll just have to remember it. So I've got the integral. I'll swap the integrand, the limits, and get a minus sign here. So if you allow me to do that, change that to a minus sign. We have 0 and I here. This is still the limit as r goes to 0. I've got an I from this, r times e to the I theta. Now when I use this, I've got just substituting this series is probably the simplest thing. So I've got b1 over, and then z minus x naught. So this was z. So it's just r times e to the I theta plus a naught plus integrating with respect to theta. So what then happens is that, remember, I'm taking the limit as r goes to 0. So these r's cancel out, but everything else is multiplied by r. So as r goes to 0, this all disappears. And I'm just left with I times the integral from 0 to pi of, and the e to the I theta is also cancelled, so of b1. So I end up with I pi b1. So in the case of a quarter circle, basically exactly the same thing is going to happen, except that rather than integrating from 0 to pi, I'll be integrating from 0 to 2 pi, so I'll end up with a pi by 2 here. So we'll end up with pi I rather than 2 pi I for the residues on the smooth part of the contour, and pi by 2 I for residues at the corners.